Yeah, thank you very much. Good morning to everybody. So you see what I'm about to talk about. I want to discuss stratification of modular representations, and what I have in mind are actually representations of finite groups. So this is somewhat in the spirit of what Shrikant presented yesterday when he talked about the Hopkins-Niemann result, which basically amounts to a classification of fixed subcategories and localizing subcategories of the derived category of a commutative ring. But today we want to do something very similar, but we want to look at modular representations of finite groups. Here on the right, you see actually sort of a main reference for that. So it is some joint work together with Dave Benson and Shrikant Iyengar. And that was a paper which appeared in 2011. Okay, so today, as I said, G is a finite group. And K is a field. And we keep that always fixed. So the aim is the stratification of KG modules. So KG is, of course, a group algebra via group cohomology. The group cohomology, which has been discussed already quite a bit, for example, in John's lectures. And the idea is that when we have modules over KG, so over K algebra, then we, of course, have a K-linear action, but we want to replace that K-linear action by the action of the group cohomology. So we enhance it basically by taking a much bigger ring. So in a sense, we replace the K-linear action on KG modules by an action of this graded ring, the cohomology ring with coefficients in K. So you remember last time in my lecture, I was basically focusing on the K-linear action and was deriving sort of various dualities. So the K-linear action is already interesting in some ways, but we get sort of more structure in this specific situation from the action of the group cohomology. So this is somehow the idea which I want to follow. And I guess I need to introduce the relevant categories, but maybe before I do that, so the relevant categories, just one sort of historical comment. I mean, that term stratification refers actually to Quillen's stratification of the group cohomology. Which is, of course, in line with the idea I mentioned already that we want to use the group cohomology. So we have chosen that term stratification of a category because we were inspired by the work of Quillen. Let me just say something sort of more historical, going further back. Yeah, I mean, the study of group representations is a very sort of classical subject. Yeah, think of Schur, Frobenius, and so on. Yeah, so it really has a long tradition. And I mean, it started all maybe with the study of characters, and then later, maybe if you think about people like Brouwer and so on, a sort of typical goal was to classify all the, say, finite dimensional indecomposable representations. There was then the notion of representation type developed. Yeah, so there is sort of a dichotomy, finite representation type, tame and wild, meaning that in some cases there's a good chance to classify all representation, namely if there are only finitely many indecomposable ones. And this is exactly when every p-silo subgroup is cyclic. That's a criterion. I think it goes back to the 1950s, Hickman. So if you develop sort of, if you follow the history, yeah, I mean, people were starting with finite type. I mean, Maschke was basically characterizing the case when the group algebra is semi-simple, namely when the characteristic of the field is co-prime to the order of the group. But then semi-simple, finite type, tame type was something done. A lot of work was done in the 1970s and 80s, meaning that there is a way to classify indecomposables, even though there are infinitely many indecomposable ones, using sort of one parameter families. And there is, then beyond that is wild representation type, meaning basically no hope to classify all indecomposables. And this can be made precise. And what we see actually when we look at representations of finite groups, that basically all the group algebras are of wild type. Meaning, I mean, finite type, I told you already, the p-silo subgroup must be cyclic, yeah, which is sort of a very special situation, of course. Tame only appears in characteristic 2. Yeah? So if you're working beyond characteristic 2, everything is wild anyway. And in characteristic 2, there's only a very small sort of portion of tame type. So what does it mean? Yeah, I mean, we have to find sort of other methods. We cannot classify all the indecomposables. And this is exactly where these ideas, say, from Quillen using the group cohomology enters. So this is sort of the historical story. And I want actually, I hope at the end to have the time for an example. I mean, I developed sort of a lot of machinery and theory, but at the end, I will really focus on an example where I look at sort of a small tame type algebra, namely the Klein-4 group, the group algebra of the Klein-4 group. Yeah, so this is what I try to cover as well. In case you get lost, yeah, I mean, there will be hopefully a nice example at the end. So the relevant categories, the point here is that we have to pass from finite dimensional representations to infinite dimensional ones because they are sort of important and you will see why. So, and this needs to be explained. So let A be a self-injective finite dimensional K algebra. And that means, so self-injective really means, so projective is the same as injective for A modules. And of course, our example is when A is a group algebra, then this is self-injective. That's known. And we look at first the category of all modules, category of all A modules. But we have already seen last time that one then can pass to the stable category, which I denote by stim-mod, but that was the same, I mean, is sort of by definition the same as this notation which I used, mod underline. And we do the same for the finite dimensional ones. So this is the category, so these are the finite dimensional A modules, same as the finite presented ones. And then we pass to little stem mod, which is the same as little mod underlined. Yeah, and you remember, what does that underline mean? We keep the same objects, but we change the morphisms. So the morphisms in the stable category are those given by this quotient, where we take the subgroup of all morphisms factoring through a projective module or injective module. Okay, so let me recall this theorem of Buchweit's. After all, a self-injective algebra is Gorenstein, and actually all modules are Gorenstein. And let me draw it like in a little diagram. So we have the projective modules, we embed them, and then we take the additive quotient, which is a stable module category. Yeah? So we kill the projectives sort of in an additive way. But we have also the derived category. Of course, we have the modules sitting inside. And here we have the perfect complexes. Yeah, and then the quotient is what one calls the singularity category. So here we take now triangulated categories, and we have the singularity category of A. And the theorem of Buchweit's was that this is actually a triangle equivalence. Because the stable module category is a triangulated category. And here we get an equivalence. Okay, we want to pass now to, as I said, we need to pass to infinite dimensional modules. And here we have to sort of discuss a recombinant. And for this, we use the category of injective modules. So let me denote by capital Inj A, category of injective A modules, which here is the same as the projective modules. But for some reasons, I mean, I can tell you, I want to think of injective modules because we will work with injective resolutions. That's it. That's the idea. The singularity category. Singularity category. So this is the singularity category. This is actually a term which I think Orlov introduced because it measures somehow the singularities. Yeah? So if the scheme is non-singular, or the algebra, I mean, in the commutative case, meaning sort of regular ring, then this vanishes. Yeah? But if not, so if there are singularities, then this category sort of captures the singularities. This is the quotient of triangulated categories. So here we take a quotient of additive categories in the sense that we just kill basically the morphisms with factors through the subcategory. And here we do things on the level of triangulated categories, or in the world of triangulated categories. So this is then the Verdi quotient. Yeah, so it's in sort of exact sequence of triangulated categories. This is an exact sequence of additive categories. No? Because this is a triangulated subcategory or thick subcategory, we can take the Verdi quotient. Yeah. Okay. Are there any more questions so far? because now I want to build up on sort of big modules. So we have, if you think about the definition of the derived category, we take the category of homotopy category of chain complexes, which is often denoted by K mod. We take inside the acyclic complexes. We take the Verdier quotient, get the derived category. This you can take as a definition. Yeah? So you take the quotient of that in the sense of triangulated categories. That's the derived category. Well, now you can also look at the subcategories. You just take the complexes of injective modules. And then you look at the sort of intersection here, the acyclic complexes of injective A modules. And you can look at that quotient. The quotient, these are triangulated categories. All are triangulated categories. You take the quotient. And it turns out, exactly as here in this situation, we obtain here an equivalence, which is not so surprising because we know that every complex has an injective resolution. So sort of we take that sort of that, yeah. What about the what? Yeah. No. I mean, think about, yeah. I mean, I was assuming here that A is a self-injective algebra. Take a module and take its Tate resolution. So you take sort of, you splice together an injective resolution and a projective resolution, and that's a perfectly nice object in this category. Yeah, I'm very glad that you asked that question because this is exactly my next lemma. We have actually an equivalence. A triangle equivalence with the stable module category, which takes a complex X and takes a complex to its cycles in degree 0, say. Cycles in degree 0. Yeah, so you have an acyclic complex of injectives, takes the cycles in degree 0, you get a module, and this is sort of well-defined up to stable morphisms. The inverse functor takes a module M to its so-called Tate resolution, Tm. This is a Tate resolution of M, where you splice together a projective resolution and an injective resolution. Okay, so if we take things together, we get actually a recombinant because there are sort of joint functors, actually. Some of these functors have adjoints, and they give us a recombinant. So a recombinant of triangulated, compactly triangulated categories. So this is a proposition. There is a recombinant of compactly generated triangulated categories. Namely, we have in the middle, we have the complexes of injectives. We have that subcategory. And because of that, yeah, So because of that observation over there, we have here the quotient, derived category, and then these functors actually have adjoints, left adjoints and right adjoints. It turns out that all these categories are compactly generated, and let's look at the compact objects. So here we know the compact objects, namely it is just the perfect complexes sitting nicely inside as a derived category of the projective, finitely generated projective modules. Here, I wanted actually rather to think of this as the stable module category. And inside the stable module category, we have the small stable module category, right? And now, yeah, you remember Buchweiz. Buchweiz tells you that there is sort of a nice extension of these categories. And in the middle, we have the bounded derived category. And this is what we get here in the middle. And actually, the left adjoints restrict to functors on the subcategories of compact objects. So here we are on the level of compact objects. Meaning here the perfect complexes, here the finite dimensional. And the only functor which needs an explanation is this one. So what is this functor? Well, it is the functor which is basically a right adjoint, which you see here, sort of. Let me call it F. And F of a complex is just its injective, sometimes called K injective resolution. Injective resolution. So if you think just of a module, you take its injective resolution, a module sort of sitting inside sort of the derived category as a complex concentrated in degree 0, you can take its injective resolution, and that would be what that functor does. It takes a module in injective resolution. And this is, yeah, what you get. So here you have really that sort of the left adjoints restrict to these functors. These are the adjoints. So recombinant means that the functor sort of in the middle here has a left adjoint and a right adjoint. Yeah, so actually the notation I like to use is, maybe we call that functor Q because it's sort of a quotient functor, Verdi quotient, so the derived category. Then Q, so Q lambda is the left adjoint. You know, I mean, the algebraic geometrists always use this Schrieg and sort of what star and upper star and lower star and so on. Can be quite confusing, at least for me. And this is a notation which Gabriel actually used. So he denoted the left adjoint of a functor by Q lambda and the right adjoint by Q rho. Yeah? The right adjoint is Q rho. It's a rho. My rho is not well written, I know. You want? Lambda and rho. Yeah, so lambda and rho give you sort of the left adjoint and the right adjoint. I mean, this is just sort of useful notation. And of course, the same here. Yeah? So this inclusion functor has a left adjoint and a right adjoint. And that these adjoints actually follow from Brown representability. So they are not sort of completely for free, but they exist. And this is sort of the statement here. What next? So we have now our sort of relevant categories, and we need to talk about the tensor structure. This theorem? Here, you mean this theorem of Buchwald's? Yeah, sure, I can, because there is sort of, in general, you remember we had the category of G-projective modules. And then we take the quotient modulo the perfect complexes. Right? So the G-projective in our situations are actually all, when A is self-injective, this is all modules are G-projective. Yeah? And now look what is actually killed. If you follow this functor, I mean, both functors are very natural. Yeah, I mean, this takes a module to the complex concentrated in degree 0. And now you kill the perfect complexes. That means basically you kill the projectives. Yeah, so if you think of this as an additive functor, it kills the projectives. So for that reason, that factors through the quotient category. Yeah, and basically this is all what is killed, only the projective. So this is sort of a faithful, and then one has to do some extra work to show it is actually becomes an equivalence. But the functors are very explicit. Yeah? And yeah, I mean, here we have a self-injective algebra, so therefore it has already a triangulated structure, so we get a triangle equivalence. Yeah? I actually, at that stage, maybe I should recommend these wonderful notes of Buchwald's, which have now been edited and published on maximal Cohen-Macaulay modules. Shrikant was one of the editors of that paper. It is sort of a paper from, I think, 1987. It was never published. It was always circulating as a preprint, and now it became, I think, in memoir. No, not an AMS text. Yeah, so it's available. Mm-hmm. It's beautiful work, and I'm glad you're asking. Yeah. Okay. So what next? I was about to erase the board. I wanted to talk about the tensor structure because it's also an important feature. Tensor structure. And this is, well, what the group gives us, tensor structure. So if M and N are KG modules, then I can take the tensor product over K, and this will be a KG module with a diagonal action, with diagonal G action. And there's a nice feature. If M or N is projective / injective, then it's sort of sufficient that one of them is projective, then this is projective / injective, which is not sort of difficult to see. So that means, so these categories we care about, namely k-inch and the stable module category, are so-called tensor triangulated. Are tensor triangulated categories. What is actually the unit? Well, here it's clear the trivial representation. So the unit here, it's a trivial representation. Obviously. Well, here, how do we think of the trivial representation inside the category of complexes of injectives? Well, we take the injective resolution of it. The injective resolution of K, sort of the injective resolution of this. No? That becomes the tensor unit. Well, now let's see how we can make use of that tensor unit in particular, the tensor structure. So the triangulated category is suspended, has a suspension, and that will be used. That means basically that all the homomorphisms so let's now work a little bit more generally. Here, triangulated category with suspension sigma. So for objects x, y, and t, we use this notation here, hom star x, y. We take the graded homomorphisms from each x to sigma n of y for all n. And if we now suppose T is now tensor triangulated category with unit is tensor triangulated, then we set R to be the graded endomorphisms of the unit, which is graded commutative in our situation, namely the examples which we have in mind. Let's here take two examples. The first example is very much familiar. If A, if equals R, is a commutative Noetherian ring, yeah, we take E mod A, so sort of T. The triangulated category has a tensor structure, and if you take the tensor unit, it is nothing but R. Yeah. So the tensor unit is just A equals R in a sense, concentrated as a complex concentrated in degree 0. And the other example, which I do care about, is for T. We take now the homotopy category of complexes of injectives. The tensor unit is the injective resolution of K, and what is R? In this case, it is the X. If you compute the endomorphisms, you compute nothing but the X algebra of K, which we identify with the group cohomology. Right? So the important point is now that then the graded homs are graded R modules. Well, this is also a valid example, of course, because it's sitting inside. So it is actually the tensor port. It's sort of a tensor ideal. It is also yeah. So stem-mod T equals the acyclic complexes. The point here is that if you look now at the unit, the graded endomorphisms of the unit in this case are the graded endomorphisms of the trivial representations. This is actually Tate cohomology. Here, for the stable module category, you get Tate cohomology, yeah, which is bigger, somewhat bigger. So that's one of the reasons why maybe it is more natural to work with this category here. Even though we care and we are interested at the end in that category. Anyway. Okay, so so we suppose now that we have such a tensor-triangulated category, and we have seen that this is sort of a good context for our examples. And now I want to talk about local cohomology and support. Basically, I want to set up some functors which allow us to define a notion of support. And this is inspired, of course, by the local cohomology functors, which one has in commutative algebra and which we have seen before. But I do it sort of now in a very formal way. So, that's the Tate cohomology. It is by definition what you get when you compute the endomorphisms in the stable module category, because you get Tate resolutions. A Tate resolution, what I meant, splicing an injective and projective resolution. And if you look at the cohomology, yes, exactly. It is infinite in both directions, yeah. Exactly, that's the point, yes. Whereas here, this is only in non-negative degrees, whereas here you have sort of also entries in negative degrees, I mean non-zero. Yeah, yeah. There is duality, so you can actually there is not much more information, if that is your question. Yeah. So, I mean, we don't want to use that. That's a message. Yeah. Yeah, yeah. Mm-hmm. So, but let's write that is Tate cohomology. So let's stick to the usual cohomology. Okay, so we denote by spec R the set of homogeneous or graded homogeneous prime ideals of R. And now let's fix a subset which is specialization closed, specialization closed. And then we define all the modules we are looking at are graded modules. And we want to define what it means that a module is V torsion so an R module, graded R module, M is called V torsion if by definition M localized at P equals 0 for all primes which are not in B. And if you think about it, it generalizes the notion of torsion with respect to an ideal, because if we take an ideal, we can take the specialization closed set of all primes which are containing the ideal I, and then this is the usual notion of I torsion. Anyway, so this is a definition which is sort of convenient because we see here we get a localizing subcategory. So the localization is exact. So we look at the mod which are vanishing here. So we get a localizing subcategory. A graded R module is M is called P local. So for prime, or a prime P in spec R, M is P local if the natural morphism M to its localization is an isomorphism, is an isomorphism. And now we take these subcategories. We look at all objects in T so that the graded morphisms from any compact object is V torsion for all compact object C in T compact. And we denote by T sub P the subcategory of all objects which are P local, and that means from C X is P local for all compact objects. So these are the V torsion objects. And these are the P local objects. So this is actually a localizing subcategory. And this is a co-localizing subcategory. So what I mean, that means that the inclusion functors have adjoints. Let me continue here. And these adjoints will be used to define the local cohomology functor for each prime ideal. So the inclusion admits a right adjoint which sends an object x to gamma v x. And here, if I take the p local objects, this admits a left adjoint. And this sends an object x just to x localized at p. So this is just a notation. And the local cohomology functor, so this is now the definition, gamma p is an endofunctor, and it takes an object x to, first I localize at p, and then I take gamma vp of this. So vp is the specialization closed set of all primes q in spec R, which contain my prime ideal given prime ideal p. So this is what I call the sort of local cohomology functor. And I know that the notation is not sort of optimal in some ways, and there have been sort of complaints about it, but in sort of special situations, we see, say, if you take a commutative ring, my first example basically here, and if it is local and you take for p the prime ideal, it is sort of giving you the usual local cohomology functor, which John discussed, for example. But this is sort of a formal definition which then also can be applied in these situations which we want to look at. Okay, and the support of an object X is now simply all the prime ideals. Remember, homogeneous prime ideals. Everything is graded. So that gamma p x is non-zero. Yeah, so this is the support on object X in T. So this is the support, and this is the local cohomology. The local cohomology functor corresponding to a prime P. So these are the crucial definitions. As I said, I recommend to look at an example as this specific example where you have a commutative ring, then this coincides with the usual local cohomology. Any questions so far? I know it's a bit abstract, but it is sort of the right concept for what we want to achieve in a sense. You know? So actually, there is a way to compute the support for X in T compact, there is sort of a way to compute this, namely the support of X turns out to be a specialization closed set. It is nothing but the support of the R module. If I take the graded endomorphisms, yes, so I take the graded endomorphisms and view it as an R module, then it is the same, in particular, it is specialization closed. Yeah, I'm assuming that actually Hom is Noetherian, which is in our situations not a problem. Yeah? So the endomorphisms of X are Noetherian. Yeah? That's that sort of a naive definition which doesn't work in general. It's too big. Because you see, for example, it's automatic, it's then specialization closed, it's a specialization closed set. But you will see, we'll have sort of objects where the support is just a single prime, which is not, in general, if the prime is not maximal, it will not be a specialization closed set. So this is somehow a more refined version of support than the usual one. I'm saying when you are in a sort of finite situation, so the object is compact, endomorphisms are Noetherian, then it is the same, as you said, the same support, the same classical support, but otherwise not. Yeah, yeah, so basically here one, yeah, no, it's a very, very good point. And now we can actually see why we actually care about this local cohomology functors. So this is a local. Maybe you should not worry about it. No, I don't know what I want to stick to. Maybe I stick to small. That's a graded R module. And for an R module, there is sort of the traditional support. Yeah, so you know what I mean. Even there are two notions. Yeah, yeah, yeah. Mm-hmm. I should have been more precise, I know. Yeah. So the local global principle is sort of our justification for looking at this. So for an object X and T, we set log tensor X, the localizing tensor ideal generated by X. So it's the smallest localizing subcategory containing X and all tensor products of X with other objects. So it's a tensor ideal. And then we have this is the definition. And then for two objects X and Y, we have that X is in the localizing tensor ideal. Remember, we want to classify localizing tensor ideals. And this we can reduce to the situation that we are in the sort of p-local p-torsion category, namely that gamma p x is contained in the localizing tensor ideal of gamma p y. And this, of course, for all primes p in spec R. Yeah, so we can test whether X is built from Y by looking at the same situation inside this category gamma P. So maybe that was also something I should have defined. So gamma p t is basically gamma vp of t intersected with tp. So these are the p local slash p torsion objects. And this is the localizing subcategory, even a localizing tensor ideal. So definition, T is now stratified by the action of R namely the tensor unit is stratified if these subcategories gamma pt is minimal for all p in spec R. So in a sense, they are the building blocks for our category. And there are the, what meaning here, minimal, either gamma p, well, I can say this has no proper contains no proper localizing. No, sorry. It has no proper localizing tensor ideal inside. Except 0. It could be 0. I mean, there are cases where this is 0. If it's not 0, there should be no other proper localizing tensor ideal sitting inside. Okay. So this notion of stratification, once we have that stratification, we can apply the local to global principle and we achieve a classification of all the localizing tensor ideals. So here is the corollary. Basically a corollary of that local to global principle. Suppose he is stratified. by R. Then we actually get a classification of all localizing tensor ideals, meaning if I have T and if I have a, say, subcategory S, I attach to it its support, which is thus the union of all the supports of objects X in subcategory S. And this is a subset of spec R. And this gives a bijection, between, yeah, all localizing tensor ideals of T. And secondly, the subsets, all subsets of the support of T, which is the same as the support of the tensor unit. Yeah, so you look at the support of the tensor unit, which equals the same as the support of the whole category, which is, of course, sitting inside. Well, now we care also about the compact objects, because we want to classify 6 subcategories, say, of perfect complexes or finite dimensional modules, stable category of finite dimensional modules. So if we take this category of compact objects, take subcategory, let's call it C. Let's take it to its support. This gives us a bijection with all the specialization closed subsets. So it gives a bijection between, yeah, the six tensor ideals of the category of compacts, and on the other hand, the specialization closed subsets of the support of T. Well, and now all the definitions and the theorems are presented in such a way that I can state the main result, which, as I said, goes back to this joint work with Lev Benson and Shrikant Iyengar. So K inch, Kg, and also stemod, therefore, are stratified via the action of R, which is the cohomology ring of K. And and the consequences, of course, you can see here. Namely, we get a classification of the thick tensor ideals and the localizing tensor ideals. And just let me remind you about the recommand. Or maybe about the Buchweit's sequence. Read? Can you just read up? Yeah, sorry. So the homotopy category K-inch, Kg, and also the stable module category are stratified. These two categories I care about are stratified via the action of the ring R, the cohomology of G. And yeah, I guess I have time. The other example, of course, not an example, but the theorem of Niemann was sort of the predecessor by Niemann. What basically Shrikant presented yesterday is that the derived category is stratified by the action of the ring itself for a commutative Noetherian. Yeah, so if A is a commutative Noetherian ring, the derived category is stratified in that sense by the action of A itself. So, yeah, there's a little time for the example, and but I wanted to remind you about Buchweit's. So what is the support? The support of this is everything. The support is basically spec of the whole homotopy ring. Here we have Pod, here we have Pod. And by Pod, I mean we have the sort of unique maximal ideal of positive degree element. So the maximal ideal of positive degree elements in the cohomology ring. And Pod just means, as usual, R is just sort of spec R without removing sort of the maximal ideal M. And here the support is just the maximal ideal. Yeah, so the perfect complexes are somewhat uninteresting in a sense. Yeah, the support is small. The interesting thing is, of course, the stable module category. Yeah. So now I have actually 5 minutes to give you a very explicit example. Namely, the Klein group. Because things can be computed. So let me take two generators, G1 and G2. So the product of two copies of the cyclic group of order 2 and K should have characteristic 2, of course. Otherwise, the group algebra is semi-simple. And if I set now Xi to be Gi minus 1, then we have Xi square equals 0, and the group algebra KG identifies with the, so I take as generators these x1, x2, and the group algebra is generated by x1, x2, and modulo the relation x1 square and x2 square. Right? So one draws modules by sort of little diagrams. For example, the group algebra is 4-dimensional. So let's denote the basis vectors by B, C, and D. So KG is sort of KA plus KB plus KC plus KD. And the action on the basis element is like this. So what does it mean? So if I have sort of a vertical sort of arrow here, and an element A and an element B, and here I write xi, that means that xi times A equals B. Yeah, so I want to specify the action of the basis element, the generators. The generators are x1 and x2, and I specify the action if it is non-zero. Yeah, so if there is no, yeah, so for example here, there is no x1 times d or x2 times d equals 0. So therefore, there is no further line drawn, right? So this is the notation. And then, for instance, the syzygies, the negative syzygies are more interesting. So this looks like this. So it's 3-dimensional. Omega minus 2 of k equals, has this diagram. And then you see already the pattern, the obvious pattern. Continues like this. So you have the zigzags. And because we can, if we know the syzygies of the trivial representations, we can already compute the group cohomology because we have the isomorphism between, so xn of k, k, so in degree n, is isomorphic to the stable homomorphisms from k to the syzygy omega minus n of k. Yeah, but with the help of these little diagrams, we can easily compute this. Yeah? And so in particular, we see that R, the cohomology, is nothing but, I mean, John has explained that already, with the degree of psi I in degree 1. Yeah? The degree of psi I is 1. So I have two generators. And now if, now I want to talk about the indecomposables. Indecomposable finite dimensional representation. So for any prime ideal, which is non-zero and not maximal, fix some generator. So homogeneous of, say, degree d. Yeah, so I fix some prime ideal, take a generator pi, then I can for any r greater or equal, well, that should be greater or equal than 1. I look now at the corresponding morphism. into omega minus r times d of k, pi to the r. So what's going on? Yeah, so the element in the cohomology ring corresponds to a morphism. A homogeneous element corresponds to morphism from K, trivial representation to a syzygy. Yeah, and then I can take its co-kernel, and this is the famous L zeta module, or here I call it L R P to the R. So this these modules have been studied a lot by Carlson, and I think he introduces notation. And now I can give you a list of all indecomposables and their supports. So the support of Kg I mentioned already, it's just the maximal ideal. Yeah, so this is the regular representation. The support of the syzygies, omega n k, is the full support. It's spec R. And so what are the indecomposables? So we have the trivial representation, the regular representation, we have this syzygies of the trivial representations, and we have these L zeta modules. So the support of L P to the N, or R, sorry, R, was just the prime ideal, prime P and M. Yeah, so remember it needs to be a specialization closed subset. Yeah, and of course we get some P1 sort of family because Podge in this case is nothing but P1, right? Or it depends how you look at it. I mean, as a scheme or as a set of points, the modules are parametrized by the projective line, yeah, because of this. So this is sort of at least one example, and I guess I should finish in. Yeah, thank you very much.
Any questions?
Mm-hmm. Yes. Yes, this is exactly what I meant. So we take now the finite dimension modules. We talk only here about now the finite dimension modules. KG modules which are indecomposable, so have no proper sort of direct summons. Mm-hmm. Yes. These are all the indecomposables. Yeah. And here you have two parameters. Yeah. So the P is basically in P1. Well, no, I mean, I should be careful. I mean, P is in spec R, and R is an integer. Yeah. So we get a sort of P1 family. Yeah. So that's the parameterization of all the indecomposables. Yes. These modules which are sort of important, they have been used a lot by John Carlson. This classification, that's a good question. I mean, it really goes back. In a sense, it uses sort of, no. I mean, yes. Rumund, he was a PhD student in Münster in the 1930s. So it is a thesis, and who was the supervisor? It was, I mean, that was not Power. It is, of course, connected to the classification. You know, we have here the polynomial ring in two variables, basically, with these relations. But you have this covering. Right, this is a covering. And the representations here can be sort of obtained by pairs of linear maps. So if you look at representations of this Kronecker quiver, I mean, this quiver is called the Kronecker quiver because basically, if you look at representations, you look at vector spaces, pairs of vector spaces in linear maps. And the way to attach a representation is basically take the direct sum of and with the corresponding action, right? And that's why Shrikant sort of attributed to Kronecker, but in this sort of setting of group representations, it was done later or yeah. Yes. 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 Yeah, I mean, if you, exactly, if you look at this, then this is already sort of a wild problem. No, there is no reasonable classification of indecomposables. And this is why one sort of puts some sort of equivalence relation on the indecomposables. Yeah? So basically you say two indecomposables or two modules are equivalent if they generate the same SIG subcategory. Or let's say the same SIG tensor idea. And then again, we obtain this classification in terms of subsets of spec of the cohomology ring. Yeah. So even though it's sort of a wild problem in general, but we put some sort of sufficiently nice equivalence relation to obtain some sort of classification in terms of the cohomology. Yes, yes. Yes. Yeah. It's already wild. What we have done to circumvent wildness and yes, yes. This is a message. Yeah.
Is the sense of the lecture at
yes.
the end?
Yes, that's a very nice summary. Yeah, that's a very nice summary. Yes. So you see, I was in the sort of early 90s, late 80s, I was a PhD student of Klaus Ringel, and he was very much, I could say, obsessed by studying tame representation type. And he said, don't look at wild type. Yeah, it's hopeless. Forget it. There's no way to classify wild representations for wild algebras. But here you see, I mean, if you change the perspective and use sort of the commutative algebra, which one has from the cohomology ring in that case, there's sort of a way to classify. Thanks for summarizing.
Any other questions? If not, let us thank the speaker.